The engineer's concern likely stems from the National Electrical Code, which typically limits the number of current-carrying conductors or circuits in a single conduit. For American wire gauge 8 and larger conductors, the limit is generally 4. For conductors American wire gauge 6 and smaller, it is often 3. This rule exists for several reasons. Firstly, heat dissipation is a significant factor. When multiple circuits carry current through a conduit, the heat they generate can raise the temperature inside. This elevated temperature can potentially damage the insulation on the wires, leading to safety hazards and system failures. Secondly, overcrowding within the conduit can create problems. Too many conductors in a conduit can make it difficult to pull and maintain the wires. This increased difficulty raises the risk of damage during installation or subsequent maintenance. Furthermore, troubleshooting issues becomes more challenging when a conduit is overly crowded. Thirdly, electromagnetic interference is a consideration. The magnetic fields generated by current-carrying conductors can interfere with other circuits in the same conduit. This interference can cause performance issues, particularly in sensitive electronic equipment. Harmonics are distortions in the sinusoidal waveform of an electrical current. They can create problems such as overheating, transformer failure, and equipment malfunctions. However, harmonics are typically not a significant concern in lighting circuits. Consider re-evaluating the engineer if the following are present. 1. They are citing the 4-circuit rule for a conduit system that contains only lighting circuits. 2. They do not understand the concept of 3-phase wiring and its implications for harmonics. 3. They are not considering other factors, such as heat dissipation and overcrowding, that can limit the number of circuits in a conduit. In the described case, it may be appropriate to use 3/4-inch conduit with 2 ports containing number 12 American wire gauge wire for 20 amp circuits in the food court. However, it is important to consider the following. Firstly, ensure that the conduit is properly sized to provide adequate heat dissipation for the number of circuits it contains. This involves calculating the total heat generated by the conductors and comparing it to the conduit's ability to dissipate heat. Secondly, use dirting factors as required by the National Electrical Code if the conduit is exposed to high ambient temperatures. Dirting factors reduce the allowable ampacity of conductors to compensate for the effects of elevated temperatures on insulation. Thirdly, follow good wiring practices, such as avoiding sharp bends and securing the wires properly within the conduit. Sharp bends can damage the insulation of the wires and increase the difficulty of pulling them through the conduit. Securing the wires prevents them from moving and potentially rubbing against each other or the conduit, which could also damage the insulation. If there are any concerns or questions, consult with a qualified electrical engineer for further guidance. An electrical engineer can perform detailed calculations to ensure that the conduit system meets all applicable codes and standards. They can also provide recommendations for optimizing the design to improve performance and reliability. When dealing with electrical systems, always prioritize safety and consult with qualified professionals to ensure that the work is done correctly and safely. Overfilling conduits can lead to several problems. The most immediate concern is the potential for overheating. When too many current-carrying conductors are packed into a conduit, the heat generated by these conductors cannot dissipate effectively. This can lead to a buildup of heat within the conduit, raising the temperature of the wires and their insulation. Elevated temperatures can degrade the insulation, causing it to become brittle and crack over time. This degradation increases the risk of short circuits, ground faults, and ultimately, electrical fires. The National Electrical Code provides guidelines on the maximum number of conductors allowed in a conduit based on the size of the conduit, the size of the conductors, and the type of insulation. These guidelines are designed to prevent overheating and ensure the safe operation of the electrical system. Overcrowding a conduit can also make it difficult to pull wires through the conduit during installation. When there are too many wires crammed into a limited space, the friction between the wires and the conduit increases significantly. This increased friction makes it harder to pull the wires, requiring more force and effort. In extreme cases, it may be impossible to pull the wires through the conduit without damaging them. Damaged wires can have compromised insulation, increasing the risk of electrical hazards. Even if the wires can be pulled through the conduit, the process can be time-consuming and labor-intensive. This can increase the cost of the installation and delay the completion of the project. Overcrowding a conduit can also hinder future maintenance and troubleshooting efforts. When a conduit is packed with wires, it becomes difficult to access individual wires for testing or repair. This can make it challenging to diagnose and fix problems within the electrical system. In some cases, it may be necessary to remove all the wires from the conduit to access a single wire, which can be a time-consuming and disruptive process. The limited space within an overfilled conduit can also make it difficult to use tools and equipment for testing and repair. This can further complicate the troubleshooting process and increase the risk of errors. Electromagnetic interference, or EMI, can also be a concern in overfilled conduits. Current-carrying conductors generate electromagnetic fields that can interfere with nearby circuits. When conductors are packed closely together in a conduit, the electromagnetic fields can couple more effectively, increasing the potential for interference. This interference can manifest as noise on signal lines, data corruption, or even malfunction of sensitive electronic equipment. While EMI is generally more of a concern in low-voltage circuits, it can still be a factor in power circuits, especially if there are sensitive electronic devices nearby. Harmonics are another potential issue that can arise in electrical systems. Harmonics are distortions in the sinusoidal waveform of the alternating current. They are typically caused by nonlinear loads, such as electronic devices, that draw current in a non-sinusoidal manner. Harmonics can cause a variety of problems, including overheating of transformers and conductors, increased energy losses, and malfunction of sensitive electronic equipment. While harmonics are not directly related to conduit fill, they can exacerbate the problems caused by overfilled conduits. For example, if a conduit is already overheating due to excessive conductor fill, the presence of harmonics can further increase the temperature and accelerate the degradation of the insulation. To avoid these problems, it is essential to follow the National Electrical Code guidelines on conduit fill. These guidelines specify the maximum number of conductors allowed in a conduit based on the size of the conduit, the size of the conductors, and the type of insulation. It is also important to consider the effects of ambient temperature and dirtying factors when determining the allowable capacity of conductors in a conduit. In addition to following the National Electrical Code guidelines, it is also good practice to leave some extra space in the conduit to allow for future expansion or modifications. This can make it easier to add or remove wires in the future without having to replace the entire conduit system. Finally, it is important to use good wiring practices when installing wires in a conduit. This includes avoiding sharp bends, securing the wires properly, and using the correct type of connectors and fittings. Good wiring practices can help to prevent damage to the wires and ensure the safe and reliable operation of the electrical system. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is designed to protect people and property from electrical hazards. The NEC is not a law itself, but it is often adopted by state and local governments as part of their building codes. This means that compliance with the NEC is legally required in many jurisdictions. Even in areas where the NEC is not legally mandated, it is still considered a best practice to follow its guidelines. The NEC is divided into chapters, articles, and sections. Each section covers a specific aspect of electrical installations. The NEC also includes numerous tables and examples to help electricians and other professionals understand and apply the code requirements. One of the most important aspects of the NEC is its focus on safety. The code is designed to minimize the risk of electrical shock, fire, and other hazards. It includes requirements for grounding, bonding, overcurrent protection, and other safety measures. The NEC also addresses the proper installation of electrical equipment, such as outlets, switches, and lighting fixtures. It specifies the types of wiring methods that are permitted in different locations and the minimum size of conductors that can be used for various applications. In addition to safety, the NEC also addresses the performance and reliability of electrical systems. It includes requirements for voltage drop, conductor ampacity, and other factors that can affect the efficiency and longevity of electrical installations. The NEC is a complex and constantly evolving document. It is essential for electricians and other professionals to stay up to date on the latest code requirements. There are many resources available to help with this, including training courses, seminars, and online forums. The NEC is not a substitute for professional judgment. It is important for electricians and other professionals to use their knowledge and experience to make sound decisions about electrical installations. However, the NEC provides a valuable framework for ensuring the safety and reliability of electrical systems. The NEC is updated every 3 years to reflect changes in technology and best practices. The process of updating the NEC involves a rigorous review and revision process that includes input from a wide range of stakeholders, including electricians, engineers, manufacturers, and regulators. The NEC is organized into 9 chapters. Chapter 1 covers general requirements such as definitions, scope, and administration. Chapter 2 covers wiring and protection, including requirements for wiring methods, overcurrent protection, and grounding. Chapter 3 covers wiring methods and materials, including requirements for conduit, cable, and other wiring systems. Chapter 4 covers equipment for general use, including requirements for appliances, lighting fixtures, and motors. Chapter 5 covers special occupancies, including requirements for hazardous locations, healthcare facilities, and agricultural buildings. Chapter 6 covers special equipment, including requirements for electric signs, elevators, and data processing equipment. Chapter 7 covers special conditions, including requirements for emergency systems, fire alarm systems, and communication systems. Chapter 8 covers communications systems, including requirements for telephone, data, and cable television systems. Chapter 9 contains tables and examples that are used throughout the NEC. The NEC is an essential resource for anyone involved in the design, installation, or maintenance of electrical systems. It provides a comprehensive set of standards and guidelines that can help to ensure the safety and reliability of electrical installations. It is important to stay up to date on the latest code requirements and to use professional judgment when making decisions about electrical installations.